Hello students, welcome back. Let us resume our discussion in section 5. Previously, we studied canonical homomorphism, which is defined like this. Let n be a normal subgroup of G, then the map gamma from G to the factor group G over n, defined like this, is a homomorphism with kernel n, which we call the canonical homomorphism or the natural homomorphism. Remember all that? Recall also that we successfully expressed the normal subgroup that we started off with as a kernel. That looks great, because we are in this very same form when we had a homomorphism and a kernel, so that the factor group is isomorphic to the image. Remember that too? That's what we established in section 4. One of the things that we established in section 4. Can we apply that here? Well, not so fast. If you do that, well, kernel is n, so k becomes n here. And the homomorphism is gamma, so instead of phi, we have gamma of g. And what is gamma of g here? Extending g to g over n, and this is clearly onto. So this entire thing is actually g over n. So that's the conclusion. The factor group is isomorphic to itself. It doesn't help much, does it? So this doesn't really work. Blindly applying 4.2 does not work. Of course, there's another reason. The circular logic I told you about in the previous video. In any case, you cannot just go back and reuse section 4. We have to re-establish and reprove everything, and that's what this 5.3 is all about, the fundamental homomorphism theorem. Let's begin. Let phi be a group homomorphism from a group G to another group G prime with a kernel K. And in a special case, when kernel K is n, we get this. But in general, it works for all other kind of things as well. Now, this is kernel, so this is normal, so we can consider the factor group G over K. And from there, let's define this map mu. Mu of GK is phi of G. What we want to do is to prove that this map mu is a well-defined isomorphism. We're going to call it the canonical isomorphism, or the natural isomorphism induced from the map phi. So, how do you prove this as an isomorphism? Well, we have to prove three things, right? Homomorphic, one-to-one, and onto. Not so fast. One more. We have to prove first this is well-defined. In this case, we didn't have to worry about whether this is well-defined or not, because this was defined in terms of each element. So for each element, we had a unique expression, so no problem here. But in this case, you have a coset. So what if we have two or more different elements that form the same coset with different outcome? If so, then everything breaks down. We have to make sure that doesn't happen. In short, we have to establish these four. Well-defined, homomorphic, injective, and surjective. By the way, before starting this, let me show you the graphical explanation of this. So, phi of G, small g, arbitrary element of capital G, is mu of GK. But what is GK? It's gamma of G, where gamma is a canonical homomorphism. So we have this picture. Gamma first, and then mu is equivalent to phi directly. Blue and then red is same as green. Or green is red composition blue. Here, gamma is a canonical homomorphism, and mu is a canonical isomorphism. And this one is arbitrary homomorphism from G to G prime. Okay, alright. That's a graphical explanation. And let's go ahead to the proof. How to prove this is well defined? This is what we have to establish. Same input, then same output. Homomorphic, that's what you have to do. The group operation is preserved here for g over k and for g prime. And then injective. Same output must have come from the same input. And finally, surjective. But this one is trivial actually, because arbitrary element of this target phi of g is phi of small g. And arbitrary small g will give me what we want. So yeah, this will cover everything there. So surjectivity is trivial. We don't really have to prove it. These three we have to. And let's begin. First, let's prove that this is well defined. How do you prove it? Well, let's consider some reduction first. So how do you reduce this g of k is equal to g to k? They belong to the same coset, means g1 and g2 are equivalent in terms of that left coset relation. So g2 inverse belongs to k. So this and that means the same thing. Now here, mu of g1k, that's phi of g1. And this is phi of g2. So instead of this, we can prove only this one, which is a bit of a reduction. Let's see, can we reduce a little bit further? Well, let's go back to this. g2 inverse g1 belongs to k. That means a certain k, which is a member of the kernel. So if I apply a certain phi here, then what do you get? What is phi of k? Where k belongs to the kernel, so the function value is the identity. It should be e prime because it's the identity of g prime. And from here, can you get that? Well, let's see. You can manipulate this one as well. Flip this phi of g2 to the other side as well. Flip to the other side, and then this is e prime because this is a group operation in g prime. Let's see. This generating that. Oh, that's easy. That's because phi is a homomorphism. Yeah, looks like everything looks good. Well, indeed, here's a proof and here's a first hint. Pretty much the same as this one here, so I don't really need this. And then let's make the first observation. g2 inverse g1 belongs to k, and g2 inverse g1 is k, where k belongs to the kernel. But this one here, there's no real progress from here to there, so let me make one more progress here. Flip this g2 to the other side by multiplying g2 to both left hand side and right hand side. And there you go. There goes the critical observation. g1 can be written as g2 times k. Or you could have written g2 as k times g1. Either way. And how do you apply that? Well, here we go. Mu of g1k is phi of g1, okay? And that phi of g1 is phi of g2k, as you saw from this critical observation, which I highlighted in purple, excuse me. And now it's pretty easy. Phi of k is just e prime because k belongs to kernel, and we end up with phi of g2, or mu of g2k. All good? Let's go to the next step. Homomorphic. How do you prove that? Well, that's going to be pretty easy as a matter of fact, because what do you mean by mu of g of k times g to k? How did you define the group operation in this normal subgroup? It is defined as g1, g2, k. That was the very definition. And then this is the same as, let's see, phi of g1 times g2. Okay? How about the right-hand side? Mu of g1k, that's by definition phi of g1. And this one is, of course, phi of g2. And is this true? Yes, it is. Phi is a homomorphism, so it is true. So yeah, that's pretty simple. And here's the full proof. No problem there, right? Next, injectivity 1 to 1. So same output must have come from the same input. How do you get that? Well, that means phi of g1 is phi of g2. And what do you mean by that? Well, we used this before. And Coulson relation, like this, or equivalently speaking, this is equal to k, which is a member of the kernel. Does it help? Yeah, it helps kind of like this. So if I apply phi here, then apply phi of k, but that belongs to kernel, so that's the identity. And as for this part, well, all you have to do is flip this phi of g2 to the other side, right? And then that's e5. And does this imply that? Yes, indeed, because phi is a homomorphism. So that's the idea. And here is a bit more efficient proof. No, not really, it's the same thing. Same thing we just did. Yeah, same thing we just did. Just written once again. Let's see, let's open this one to surjectivity, even though this is trivial. And there goes the full proof. So, we successfully proved that this map mu is well defined, and then it's an isomorphism. We call it the canonical isomorphism. And let me show you the graphical expression once more. From G to phi of G, that's arbitrary homomorphism, that can be re-expressed in terms of phi G to G over K, the kernel, and then G over K to phi over G. And this is canonical homomorphism, and this one is canonical isomorphism. Okay, that completes 5.3, and I don't think we have time to do an example problem, so let's stop here, and let's do the example problem in a separate video.